Hello. So, we have this example question here that you might see on a midterm. What is the total capacity of a memory with addresses coded on 1 byte and memory words of 16 bits, and how many instructions can we define in this system? So let's start off by writing down what we do know, and we'll go from there. We know that the address is made up of 1 byte. What is 1 byte? It's basically 8 bits, or 8 binary digits, and you have seen these so far. They're basically either a 0 or a 1. And we have 8 of those to represent the address. So it would look something like this maybe. You have 8 bits representing it. Now, 8 bits is equal to 2 to the power of 8, or 256 unique addresses can be represented with these 8 bits. Then we have our memory word. Our memory word is made up of 16 bits, which, how many bytes is it equal to? 2 bytes. Although that's not really necessary. But we're going to write it down anyway. So we have an address of 1 byte, or 8 bits, and a memory word of 16 bits, or 2 bytes. Now what do we need to do in this question? We need to define the total capacity, and we need to see how many instructions can we define in this system. So let's write that down. We want the total capacity, and we want the amount of instructions we can represent. So let's represent this visually so we can, solve it a little easier. We have our address, and the address is made up of 1 byte, or 8 bits. And on the right, we have our memory word, and it's made up of 2 bytes, or 16 bits. So, what can the memory word represent? The memory word can either represent some sort of data, whether that be an integer, signed or unsigned, whether it's a float, whether it's something else, it doesn't matter. It's some sort of data. Or it can represent an instruction, right? So something could go to this address and find an instruction, and it has an address and some sort of operation it's supposed to accomplish at that address. So let's now calculate the total capacity of the system, and there is a formula we can use to do that. It is 2 to the power of the address times the memory length. So why do we use a 2 here? Well, it's because we're working in a binary system. So we can only represent something with either a 0 or a 1. In this case, it will be 2 to the power of 8, because the address is made up of 8 bits, or rather, in here, there are 8 positions, and each of them can either be a 0 or a 1. To get the total capacity in bits, we then multiply it with the word length. Not 2 to the power of the word length, but times the word length. So in this case it would be 16. Now, to make this simpler, what we're going to do is we're going to reformat this a little bit. So it's 2 to the power of 8. Now we need to find 2 to what power is equal to 16. So 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3, 4 times 2, that's 8, 2 to the power of 4, 8 times 2, that's 16. So 2 to the power of 4. And we can continue calculating. To make things easier on us, this is how we're going to calculate it. We have 2 to the power of 10 times 2 to the power of 2. Now why do we use 2 to the power of 10? It's because when representing data, 2 to the power of 10 is equal to 1 kilobit of data. Not kilobyte, kilobit. So 2 to the power of 20 would be equal to 1 megabit. And then 2 to the power of 30 would be equal to 1 gigabit. – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –– – –– – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – – –– and so on and so forth. So we now know that this is 1 kilobit times 2 to the power of 2, or it is equal to 4 kilobits. Because 2 to the power of 2 is 4, and so on and so on. So we now know that this is 4 kilobits. What would it be in bits? Well, 1 kilobit is equal to 1024 bits. So this would be 4 times this, which is equal to 6, 16, 2 to 4, 8, 9, 0, so it would be 496 bits. How would we calculate this in bytes? Well, the process is pretty much the same. You take 2 to the power of the address, 8, times the bytes. In this case, we have 2. Now again, we simplify. There is an invisible 1 here that we do not see, and we add. So it's 2 to the power of 9, or 512 bytes, or half a kilobyte. So I do want to draw attention to something here, because you will be working with different units of measurement. We're working with data here, so 1 kilobit would be equal to 1024 bits, or 1 kilobyte would be equal to 1024 bytes. But in other cases, when we're not working in the binary system, so 2 to the power of x, it would be 10 to the power of x. A kilo is equal to 1,000. A mega is equal to 1,000,000, or whatever. And so on and so forth. So it would be 10 to the power of 3, 10 to the power of 6. But we are working in data, so it's 2 to the power of 10, or 2 to the power of 20. So that's equal to 1024, and so on and so forth. So remember, when you're working with data, 1 kilo is equal to 1024, or 1 mega, or 1 giga. But when you're working with other units of measurements, and you're using the decimal system, it's 10 to the power of 3, or 10 to the power of 6. And it's equal to 1,000, or 1,000,000, or whatever it is. So be careful when you're calculating stuff like this. So now we have the total capacity, right? It's equal to 4 kilobits, or 512 bytes, or 4,096 bits. Now it's time for us to calculate the amount of instructions that we can define in the system. And it's pretty simple. So we know, like I mentioned earlier, that a memory word can either contain data or an instruction. Now, our memory word in this case is made up of 16 bits. So how many instructions can we define? We have a 16-bit memory word, and we have the address. Every single memory word is made up of an address and an opcode, or an operational code, which instructs the computer on what to do at that specific location. So you have adding, subtracting, storing, loading, saving, whatever. It depends on whoever manufactures the CPU and how they define it. So we already know that our address is made up of 8 bits. So that's half of our memory word. We know that the other 8 bits are used to define this operational code. So to calculate how many instructions we can do, our opcode is made up of 8 bits, so 8 binary digits that can either be a 0 or a 1, 2 to the power of 8, since we have 8 bits. So in this case, we can define 256 unique operations. There we go. What is the total capacity of memory with addresses coded on 1 byte and memory words of 16 bits, 4 kilobits, 512 bytes, or 4096 bits? And how many instructions can we define in this system? 256 unique instructions.